Yeah. So everyone, hi, I'm David. I'm a first-year PhD student at the LMU in Munich, and yeah, I'm coming from more of like an exoplanetary atmosphere background, and I'm exploring the habitability of exomoons around the free-floating planets. So yeah, basically having models of their atmospheres. And yeah, similar to me, when I first started the project, you may ask yourself, what life without a star? How should that even work? But yeah, so it can maybe work. So as we learned already yesterday and today also, is that a lot of the free-floating planets actually get ejected out of a planetary system. And this is actually really good for our case because through this ejection, the orbits of like possible moons of these planets get excited and they get a higher ellipticity. And this ellipticity is what creates the tidal heating. So we need some kind of other energy source instead of the star, yeah, to have enough temperature, sufficient temperature for liquid water, and then maybe life. And in this case, the tidal heating is what provides this. And so if we have here this slightly elliptical orbit, yeah, we can see that the planet kind of gets like squeezed and squished and stretched, and through the like internal friction, this creates the heat in the planet. And yeah, because I just started the project, I first want to start with some previous work of a colleague, so Giulia Rocchetti. She already also has a paper out on the topic if you want to know a bit more details. She basically simulated the whole process from the ejection of the free-floating planets to the simulation of the orbits and the tidal evolution to also some simple atmospheric model. And yeah, but she started with the ejection process. So she did some n-body dynamical simulations of the ejections of giant planets. Started with unstable configuration, as we learned also already, I think yesterday. Having like 3 giant planets in a system is really unstable. So that's what she did, and then looked at the impact parameters of the last close encounter. And here are some like 2 representative cases of a really low and a relatively high impact parameter on the left and on the right. After the n-body simulation, she basically injected the orbits of the moons right before this last close encounter. To then see how this last close encounter, which led to the ejection of the planet, influenced the orbits of the moons. And here we can just see the distribution of the eccentricities of these orbits. And we can see that for the higher, on the left, for the higher, and for the lower impact parameter, so where the planets get closer, of course, less of the moons survive. So more of the moons get ejected out of their orbits. We can see the green relative to the blue curve. There's about like a 30% survival rate, right? When for the like higher impact parameter, there's a 75% survival rate. And if we now compare the green to the red curve, we can see that after the ejection, as I said, these orbits get excited and they move to higher eccentricities and provide then this more tidal heating. We can see the same distribution basically here on the y-axis, the eccentricities, and on the x-axis, the semi-major axis of these orbits, of the surviving orbits. And then on the right, you can see the tidal evolution after 10 billion years. And you can see how the orbits slowly circularize, and therefore the eccentricity decreases. And then finally, these orbits were used as inputs to, yeah, again, calculate the effective temperature provided by the tidal heating, and then some simple temperature profile. Here she assumed a pure CO2 atmosphere and a simple 2-part radiative and convective temperature profile to calculate the surface temperature, and then compare the surface temperature to the range of liquid water for the respective surface pressure. And she tried out 4 different surface pressure from 0.1 to 100 bars. And we can see then the distribution of the moons of the time spent in the habitable zone here in this plot, with the maximum times indicated here, and only for like really high surface pressures. So basically for a really thick atmosphere, we get like really large timescales. So for 10 bars, we get nearly 300 million years of maximum time spent in the habitable zone. And for 100 bars, we get 1.6 billion years, which is already the right scale is similar to Earth, but still a lot less than, of course, compared to how old the Earth is. But there was one problem with this model, which we found out afterwards, is if we look at the temperature profile of the which Julia used relative to the condensation curve of CO2, we see that a lot of the temperature profiles, or at least part of the temperature profiles, lie below the condensation curves. So this would mean that CO2 would condense, and a lot of the atmospheres would become unstable and maybe collapse, which you can imagine atmospheric collapse, not so great for habitability. Then here you can see, so I did a bit of a reanalysis. On the y-axis, you can see the different surface pressures. In red, I indicated the unstable configurations, and in green, the stable configurations. And you can see here the distribution of the surface temperatures, and the blue shaded area is the where the liquid water could be. And yeah, we can see already here on the left, after 1 million years, that at 10 bar and 100 bar of surface pressure, there are basically no stable and habitable conditions. And we can see that after 100 million years, there are no stable configurations at all, unfortunately. So as first part of my project, I tried to produce a stable and hopefully also habitable atmosphere. And I want to make sure that I use an accurate pressure temperature profile. So I use a 1D radiative transfer code Helios. And then I already tried out like some different chemical compositions, but first assuming the chemical compositions, then calculating the radiative transfer and the temperature profile, and then checking afterwards if it's stable. We can see that it's hard to produce a stable atmosphere. So I try to use here, make a stable atmosphere basically from the beginning. And so I use some stable background gas, so for example, hydrogen or nitrogen, and then saturate it with one other molecule, so for example, water or CO2. This could, of course, also mean, so the saturated basically means that it's the maximum mixing ratio possible at a certain pressure or temperature. This could, of course, also mean that it is 100% of this molecule with no background gas necessary. Keep that in mind. And some assumptions coming also from Julia's model is here I use an Earth-like moon around a Jupiter-like planet. And I restricted myself to surface pressures of 1 and 10 bar, because here we saw that 0.1 bar is definitely like insufficient to retain enough heat. And 100 bar is already like really close or even above the critical point of CO2, which could also be then problematic and make everything more complicated in the atmospheric model. And here, just relatively simple, you can see the different compositions. So, for example, if we look at the first two curves of hydrogen and hydrogen with saturated water, and here you can see the surface pressure dependent on the internal temperature provided by the tidal heating. And you can see actually that the blue and orange curve, these two cases of hydrogen and water, are the best case scenarios. So they trap the heat most efficiently, as we can see here already with an internal temperature provided with 100 Kelvin at 10 bars. We are inside the habitable zone. And you can see that for example, methane in green or CO2 with hydrogen in red, provide a lot less heating. You may ask, okay, why is that that it can retain a lot less of the heat compared to like the blue curve of the pure H2. And again, this is because the lower parts of the atmosphere are then basically pure CO2 or pure methane, where no hydrogen is present if the temperature is high enough. And so the collision-induced absorption by hydrogen provides, can trap the heat more efficiently. I want to look at two cases. So here I want to illustrate this effect, which I just mentioned. In the blue curve, you can see again the methane. And because methane has a really low temperature or condensation curve, it's basically pure methane at the bottom of the atmosphere, which doesn't trap the heat so efficiently compared to hydrogen. So if I here in the orange graph, I restricted the mixing ratio of methane to 0.1. So I always have both hydrogen and methane present. And then we can see that, yeah, it traps a lot more heat. So having a more diverse species, more diverse chemistry, where different chemical species cover different wavelength ranges in their absorption spectrum, traps, of course, more of the heat and is then beneficial to our case. And here's also the comparison with CO2. We can see that with hydrogen compared to nitrogen, yeah, this can trap the heat more efficiently. And again, at the higher temperatures, we can see that the two curves become the same because it's basically pure CO2. And so I also updated here these plots on the time spent in the habitable zone. Yeah, we can again see that, of course, the hydrogen and the water case spend the most time in the habitable zone because they trap the heat most efficiently. And at least we get similar orders of magnitude. So for the 1 bar case, we have a maximum time spent in the habitable zone of about 10 million years compared to Julia's 50 million years. And for the 10 bar case, we have around 100 million years compared to Julia's nearly 300 million years. So at least same order of magnitude, just a factor of a few in between these two. And so yeah, it's a short summary. At least we see that a stable atmosphere is possible. We can see that the background of H2 can trap the heat most efficiently. The best combination was the hydrogen and water. And the exomoon can remain in the habitable zone for up to 10 or 100 million years for surface pressures of 1 or 10 bars. And there are a few factors which could even prolong this time. As I just mentioned, having the more like diverse chemistry can, of course, prolong this time. So this is also what we want to do maybe next, have some equilibrium chemistry code, which we can like connect to the radiative transfer code to also get a more like realistic atmosphere, ideally also with condensation. And what wasn't considered so far in the models of the orbits of the moons were interaction between the moons. So each orbit of the moons was considered by its own in its tidal evolution. So if they also would interact with each other, similar to the moons of Jupiter, they have some orbital resonances, so they could stabilize each other at a specific eccentricity, and so they could provide tidal heating for a lot longer time. And yeah, that's already it. I mean, a bit faster than I expected, but yeah, thank you.
Any questions? Cool.
Awesome talk, David. So one question that I had is, this was all focused on sort of defining your habitability based off of liquid water on the surface.
Yeah.
Is that the idea? Okay.
Yeah.
And so this was trapping stuff within atmosphere. Obviously, people spend a lot of time thinking about the moons of Jupiter and Saturn as potential places for life, in subsurface oceans and that sort of thing. So do you know how these numbers change if instead of trying to trap things with an atmosphere, you have some icy crust and maybe some liquid water ocean beneath that?
Yeah, so we haven't specifically looked at that, but I would say, yeah, that's probably the more likely case for like smaller moons to have these icy moons relative to similar to Jupiter. I would actually say probably there's not that much of a difference because the subsurface ocean, I mean, gets protected by the icy shell. So if it's now in a far out in a solar system, or if it's floating around somewhere in the galaxy, there's probably not that much of a difference. And so we focused more on this case of a Earth-like moon. Yeah, because there's really a stronger difference between having it like close to a sun and just floating around somewhere in the galaxy. Yeah, but this is obviously a significant case where also life could emerge.
Well, cool talk. This is interesting stuff. I was wondering, does the effect of the internal heat source like from radioactive decay of long-lived radionuclides helping you?
Yeah, I think there was also one previous paper before Julia which looked at this effect. And I think, but the tidal heating provided a lot more heat, and the more like significant part than the radiogenic heating was just
Yeah, it's gonna be more,
basically
it just wouldn't
insignificant.
last as long.
Yeah.
I was wondering if it helps to have a little bit.
Yeah, maybe at the beginning. Yeah.
Any other questions? Okay, well, I guess we have a coffee break until 3:10. So